My screen now.
Yes, sir.
Okay, so let's go into the lesson. So today we'll be treating hydrodynamics and temperature. So hydrodynamics and temperature. Some places you will see that fluid dynamics. So it's usually talking about fluid in motion or liquids in motion. That's what hydrodynamics is talking about basically. So I remain myself, HQ, and let's head into the lesson. So first, in this lecture, we'll be trying to explain the concept of hydrodynamics and temperature, and I'll try to see how much you can be able to explain concepts like the Bernoulli's principle, surface tension, viscosity, and also temperature. We'll talk about how to switch temperature from different temperature parameters like Fahrenheit to Kelvin to Celsius, stuff like that. So we're learning stuff like that. So and each session would include both examples that are typical to our JUPEB exams, so that we can be able to see how these kind of questions are being coined. So let's head into the lesson. Starting off, I'll be explaining the Bernoulli's principle. So this principle tries to explain that an increase in speed of a fluid occurs simultaneously with a decrease in pressure. So what's this saying? Saying that when we have a fluid and the fluid is probably flowing within a pipe, if the fluid is increasing by speed, if the speed of the fluid coming out of that distance of the system is increasing, the pressure would decrease. The pressure within that system would decrease. So it will decrease. And the Bernoulli's equation has this formula: P plus 1 all over 2 density times velocity squared plus density times acceleration due to gravity times height. So we can see, that's what we can see here. Here, this is the Bernoulli's equation. We have P representing pressure. This one that looks like P is curvy, representing fluid density. V is representing our velocity. G, acceleration due to gravity, and H representing the height of the system, or the length in some cases. So this equation is one of the fundamental equations that helps to understand fluid dynamics, and is usually trying to explain the dynamics of fluids in pipes or systems that are elongated. When we have fluids flowing through, we have different fluids, either gaseous fluids or liquid fluids flowing through a pipe. You can use this principle to try to determine either the density of the liquid or the fluid, either the speed at which the fluid is moving or the pressure that is within that system. So basically, this is what these formulas are. This formula is really used for measuring. The questions will usually be asked, you'll be usually asked for is to see how to get the pressure, the fluid density, or the velocity in most cases. These are the parameters you'll be asked to find. In rare cases, you'll be asked to find the length of the pipe or stuff like that. In rare cases, you'll see stuff like that. But mostly, these four are the variables for this Bernoulli's principle. So this equation you are seeing up here is known as the Bernoulli's equation. So let's see how questions are being coined from this topic. So we have our problem one, or example one. The question says, a fluid is flowing through a pipe at point A. The velocity of the fluid is 3 meters per second. And at point B, the velocity of the fluid is 6 meters per second, meaning we have a pipe, we have a pipe, and at point A, it has a velocity. By the time it moves to point B, it has a different velocity. So this expression, this question now, you're asking us to find the pressure at point. You're asking us to find the pressure at point B. So let's see how we would apply this equation solving equation. So there are 3 steps. The first step will be trying to use the Bernoulli's equation. The next, we'll try to substitute the given values that we're given for the question. And then we'll see how we can use it to get pressure at point. So let's head into the solution. So first off, when you see a question like this, you would split this equation into 2 halves. This is 2 halves. Here we have the equation here. This is the equation. So we'll put it as A point being equal to the B point, the same thing. So when you see this constant now, is going to be constant when the velocity did not change. But once the velocity is changing, let's see how we'll solve this. Let's see how we'll solve this equation. Because I was saying, I said you would have, once you have an equation where they are giving you 2 points, once you're already seeing that you are given 2 points, what you would do is you would take this equation and put it on both sides. Put on both sides. Because now we have point A, we have a point A, and they gave us parameters for point A. We have point B, and we also have parameters for point B. So meaning this equation, we will take this equation being equal to the same equation, but now the first case will be for point A, the second case will be for point B. So meaning the pressure on this side will be the pressure for point A, density on this side is going to be density on point A side, velocity, the same velocity on this side. The same, this is what you apply both on this side and on the other side. So point B, every parameter that is in point B is on this end. So let's see what I mean by all this I'm saying. So now we have this is our normal formula. Our P plus half density V squared. But in this case, when you're seeing this dash A is meaning for at point A squared equals to P for point B, EV squared. So now the only thing that disappeared was this. Because now in this case, the fluid did not talk about the height. They did not mention anything about the height. So they did not mention that the fluid is moving upward. So this parameter will come into play when the fluid is moving upward. So when the fluid did not say the fluid is moving upward, there is no gravity that would apply to that fluid. So in that case, this parameter will be unnecessary because they did not give us
Sir,
height.
please, I was thrown off.
Okay.
Please, I got lost
So
where you said that if the velocity did not change, that it will be constant.
okay. Okay. So in this kind of condition now, if the velocity of the liquid did not change, of the fluid did not change throughout the flow period, you can use this formula like this. But when the velocity is changing, or maybe the pressure is changing, that's when you would need to use this formula. But in 2 cases, you put the first case on the left-hand side, then the second case on the left-hand side, on the right-hand side rather. So now we have this same equation on the left-hand side and the same equation on the right-hand side. But now this P now will not just be ordinary P, it will be PA. This density, since it's the same fluid, the density will be the same. Then the V, that will be the velocity at point A. Then on the other side, the velocity at point B. So let's see how this thing would apply. So here we have for pressure, we have PA plus half density BA squared. We're supposed to use the other portion of this. We're supposed to use this portion, but since they did not give us height, we assume that the height is 0. And when the height is 0, all this will turn to 0. Once the height is 0, all this here turns to 0. So for that reason, the equation will now be reduced to just this. So the equation now, using that equation now, we can now see that our PA plus half density VA squared will be equal to PB plus half density BB squared. So our PA, they gave us our pressure at point A. Pressure at point A was 200 Pascal. Point A is 200 Pascal. If the pressure at point A is 200 Pascal, that we've got our PA. So now our PB is what we are looking for. They say pressure at point B, that we are looking for. We don't know our pressure at point B. So now, but they gave us the velocity at point A. The velocity of the fluid at point A, the velocity is 3 meters per second. So we already know our VA. At point B, the velocity is 6 meters per second. So we know our VB. So we know our VA, we know our VB, we know our PA, but we don't know our PB. So we can apply the formula now. So we can see on the formula, we can put in our PA, and put in our VA. We cannot put in our PB because we don't know PB, that what we're looking for. Then the VB, we also we know that dB they gave us on the question as 6 meters per second. So now, in this kind of question, now, even if they did not give you the density of, even if they did not give you the density of liquid, the density can cancel out on both sides. The density can cancel out on both sides, but leaving that aspect of density canceling out on both sides, the density, when you did not mention the liquid, most likely it's best to use the liquid to be water. So the density of water is usually 1,000 fluid. Sorry, 1,000 gram per liter cube. I don't know if you guys are still following me. This is the form. This is how we use the Bernoulli's equation. When we are given, or when we have two different points or different states, we would put in the pressure. We would need to use the formula in this format, where we would impute the first parameters at a particular point on the left-hand side, and the second parameters of the same equation on the left-hand side for the second condition. So now doing that for this equation, we'll be having PA plus half density VA squared equals PB plus half density VB squared. So why we did not use the other portion of this equation that had density GH is because our height, they did not give us any height. So our height is assumed to be 0. So we did not have any height change, only movement on the horizontal. So we do not have any height change. So that's why this is becoming 0. Once h is 0, this parameter will disappear on both sides. So that's why we have the equation to just be shortened to this form. So then putting in our parameters, we have our PA to be 200. We have our density to be 1,000 because we assume the density to be water. We have our our velocity at the initial point at point A to be 3, and so on. So we have all these parameters to be this. So we should resolve this, first solving the left-hand side. Once we've solved the left-hand side, we'll be getting an expression that looks like this. We could collect like terms or just rearrange this, take this one to this other side, take to this other side, and solving that, we'll be able to get our final answer to be this. And our final pressure will be minus 13500. That is minus 13,500 Pascal. So you could do it by your own self on calculator and see whether you get the same answer. So that's the solving. I believe you understand how we apply the formula. You said? Sorry, I didn't really get you.
To try it out. To try it out.
Okay, I didn't really get you, but let me see whether I can repeat the whole procedure again. So, first off, we know the Bernoulli's equation. This is the Bernoulli's equation, and this is what the formula looks like. It says the formula is equal to this when everything is constant. So now, when things are changing now, the formula will then be equal to itself, but now with the change on the other side. The changed parameters will be on the other side, while the other parameters, the initial parameters will be on this side. So it's just like as you're saying, this formula, when the things are changing, this formula for initial equals to this formula, the same formula for final. So now in the case, in this question we are not given a change in height. H is representing height in this formula. So since we're not giving height, we assume that the H is given as 0. So becoming, for H being 0, it means that this parameter will disappear both on both sides of the equation. So we'll be left with just this portion of the equation, P plus half density V squared. So P plus half density V squared is what we have as the parameter. So we would duplicate this on both sides, both on the left-hand side and on the right-hand side, because we had change. At point A, we had a change in velocity at point B. So things were not constant throughout the process. So because things are not constant throughout, we have to duplicate this on both sides. So that's what we did here. We duplicated that on both sides, where each of the parameters that we're varying will change on both sides.
So please bring out
So
the
pressure
equation, the formula, the first formula.
okay, this is the formula here. It should be on the slide I sent you. So we would not really spend much time. P plus half density V squared plus density GH equals constant. So you could cross check it from the slide. It's the same slide I'm using. So now with that, we apply the formula here. putting in all the parameters, we know PA, we know VA, we know the density. We assume the density that the liquid should be water. So the density of water is always 1000 in SI units. So we don't know PB, we're looking for PB,
You
but we
have
know
two P,
VB.
you have
So,
two P there. Which one is density and which one is pressure?
okay, the P that looks like real P, like capital letter P, that's this one here, is pressure. While this one that is looking somehow, that looks like as it's funny, somehow is different from this one. That one is density. So see it here, see the differentiation here. We have this here. This one, the real P, representing pressure, while this one that looks like this is representing fluid density. So that's the difference. So you could write it in a way, when you're writing it in your notes, write it in a way that you will be able to understand it. So that's it. So let's see, with that, if you solve this, putting all the parameters correctly, you should be getting minus 13,500 as your final answer. So this shows that there was a decrease in pressure as the fluid moved from point A to point B. So it shows that there is a decrease in pressure as the fluid moves from point A to point B.
I don't understand
So
how
let's move on to the next.
from the question it said plus half PV. Plus half PV, but when you are solving it, we have a V raised to power 2. So it's different from the first equation.
You understand this
The
equation here?
V
You are
is
seeing
the
what is here now.
thickness in bracket.
This V, in the case of at point A, the V is called VA. At point B, the V is called VB. That's why we have VA here.
I understand
Raised
that
power
one.
square. That's VA square. So where is the confusion?
The confusion is that now and
Hello?
you should mind yourself. Hello?
Hello?
I said
Yeah?
that, can you hear me? I
I can
said
hear
that
you.
where I'm confused is the V, you raise it to power 2. But from the question, it's not like that.
Yes, from the formula, there is V squared. Formula has V squared. So that's why we raise power 2. Are you seeing the formula?
It's not what
The
I wrote
formula has
here.
V squared.
V
So just check. The
plus
formula has V squared.
half V squared.
Yeah, so that's the formula. So you could solve and cross-check once you get the final answer. So because of time, let's see whether we can speed up a bit. We don't really have much, but let's see whether we can cover up. Then later on, if there's any confusion at the end of the class, we can be able to sit back and see whether we can deal with the confusion. So just so long as you can see it, if you are solving, just keep solving and let me see whether I can move on. Later on, maybe if I ask a question, if you are still confused, go back to these points. So for the sake of time. So now we have the next portion of this lesson is talking about surface tension and viscosity. So surface tension, by definition, is the force that acts on the surface of a liquid, which causes liquids to behave like a stretched elastic membrane. So this is a simple definition for surface tension. So is this surface tension that is responsible for why some kind of flies can stand on top of water, some kind of insects can stand on top of water. You'd have seen some cases where you see an insect stand on top of water and the water will be moving. The insect will not see sink. So it's due to the presence of surface tension that this is possible. So surface tension is just like a force that's trying to act a liquid surface. You just imagine that there's something that is pushing the liquid upward. From inside the liquid, there's a force that is pushing the liquid upward. So that force that's pushing the liquid upward is what is known as the surface tension. The force that is acting on the surface of a liquid is what is known as the surface tension. So by definition, I said it is the force that acts on the surface of liquid, which causes the liquid to behave like a stretched elastic membrane. Or some people will say, which makes the liquid act like as if it's a solid. So it is responsible for the phenomena like water droplets. So this surface tension is what is responsible for what is called for seeing stuff like water droplets, where you see like what we can see in this image, water staying on top of this leaf is not flowing, it's just staying as drop, like a ball. Normally water is supposed to stay as a drop, supposed to flow down, it's supposed to just flow, it should not stay as a ball, but because of surface tension, we can see stuff like this. So it's also the thing that is responsible for us seeing insects walking on water. So another parameter that we'll be talking about here before we go into their formulas is viscosity. So viscosity is, on the other hand, the resistance of a liquid to flow. So when you see a liquid that you're trying to pour it, it's pouring slowly. Liquids like oil, liquids like thick jelly materials or thick jelly fluids, these liquids, they are said to have high viscosity. So viscosity is the resistance that a liquid is trying to that a liquid possesses, trying to restrict it from flowing. I don't know if you guys are with me.
Yes.
I don't know whose mic is on and is making a squeaky sound. I don't know. If your mic is the one that's on, probably just turn it off. And maybe when you want to talk, just turn it on so that it will not affect the recording later on when we are playing.
Sorry,
With
sir,
that
I
being said,
forgot.
viscosity is
Oh,
okay, no problem, no problem. So viscosity is the resistance to flow by a liquid. It's the resistance to flow. So it is what we see in stuff like honey. You know, honey, if you try pouring honey it does not flow freely like water. If you try pouring water will flow off fast. But if you try pouring honey, it will take time. You pour it and it would waste time before it will pour. Especially a good honey to spend time while it's trying to flow. So the phenomenon that is responsible for this is called viscosity. So it's a measurable parameter. It's a measurable parameter in cases of fluids. So let's go to the formulas for surface tension and also the formula for viscosity. So surface tension, it has a formula that says force, that the surface tension of a liquid is equal to the force, the applied force over the length. Applied force over the length. Applied force over length. That's the formula for surface tension. While the formula for viscosity is given as the force over the product of area times velocity. This is the formula I'm putting here. I'm putting this formula. Viscosity is equal to the force all over area times velocity. So take note. I didn't write the meaning I didn't really write what A and B represent. A represents area, the area or the flow area, while V represents the velocity. So write it down in your notes so that you will be able to reference it later, since I did not put it down on this slide. So even for those that are taking screenshots. So surface tension is given as force over length. Then viscosity is given as force over area times velocity. So let's go on to how examples come up with this topic. So I don't know if everyone understands viscosity and surface tension. I don't know if you understand what
yes.
viscosity is or you can relate to it. Okay. So what would make a liquid act like as if it is strong, that you can drop something on top of a liquid and it will stand, is what is surface tension. Or you can drop a liquid on top of something and it will stay without flowing. It's surface tension. But what is making a liquid flow slowly is called viscosity. So what makes a liquid flow slowly is the viscosity of that liquid. So let's see. We have two examples here. The first example is under surface tension. The second example is under viscosity. So for the question under surface tension, you will see the question typically like, it will say if a droplet of water with a surface area of 0.5 centimeters squared experiences a force of 0.03 Newton. Calculate the surface tension. Calculate the surface tension. So now, in this case, we can see that they gave us the surface area of the liquid as 0.5 centimeters squared, and they also give us the force. So typically, you're supposed to just plug and play, just put in the formula and you should get your final answer. But because of the fact that we're given centimeters squared, because we're giving centimeters squared, you will not just use it like that. You will not just use it like that. You will need to change centimeter squared to meter, meter squared, and that is dividing it by 1,000. So when you divide it by 1,000, you can then plug it into the formula of force over length. So normally it's force over length, but some cases you might see it as force over area, depending. But the length that they're talking about is the length that the material that is being placed upon the liquid is occupying. So when you are given area, you can use the area straight up. But when you are given length, you can also use the length straight up, because surface tension, when you talk about length, when you're talking about a material that is placed on top, when you're talking about the area, when you're talking about a liquid in form of droplets. So when you're talking about something, maybe placing a needle on top of a liquid, you talk about the length of that needle, because that needle does not have an area per se. So, but when you're talking about stuff like maybe you're dropping a square material on the surface of a liquid, that square material would have an area. So in that case, you will not just talk about the length. So you have to mention it as the area. And when they give you that way, the surface tension can be used that form as the force over area. So surface tension can be used as force over area when you are given a material that has an area, and can be used as force over length when you are given materials like thread. When you place thread on a liquid, thread will stand on. For the thread, you cannot tell the area of the thread, so you can use the formula as force over length. I don't know if anybody is getting what I'm trying to explain.
No, sir. Sir, please repeat it.
Okay. In cases when you're trying to determine the surface tension on a liquid, and the material you are given is a material that you cannot tell the area of that material, you would use the formula that I gave here as surface tension being equal to force over length. So you use the length of that material, like thread. When you put a thread on top of liquid to stay, you can determine the surface tension on that area of liquid. You can determine the surface tension by knowing the length of that liquid thread. So you can be able to tell the surface tension of that liquid by knowing the length of that thread. So we are using length in that case because we cannot tell the area of that thread, because the thread is usually very small. Even needle too, when you place a needle on top of a liquid, you cannot accurately tell the needle's area, but you can tell the length of that liquid because it's the length that occupied more space. So because of that, you can then use that length as the formula. That's T being equals to F over L. But in cases where you are given materials that have area, or we're talking about stuff like water droplets is a circular material, so it does not have length per se. So in that case, you use area, force over area. So the same formula, but in that case, L will be replaced with area. I don't know if you understand me now.
Yes, sir. Yes, sir. Thank you, sir.
Okay. So once you are given the question, make sure your parameters are always in SI units, which I mentioned. I think I mentioned it in the last class. One of the things you should always observe is ensure that your parameters are in SI units. All your parameters are in SI units. So you should know SI units, what SI units are. Pascal, Newton, all those ones that has Newton per something, this one per that. Like those ones are SI units. But when you are seeing something like centimeter is only gram that can be taken as kilogram in SI unit. Only gram that is taken as kilogram in SI unit. For every other parameters, you see them in kilo this, milli this, and centi this. They are not in SI unit. Only gram is meant to be in kilogram for SI unit. Length is supposed to be meter, not kilometer. I don't know if I'm communicating that, yeah. So let's move on to the second example. So if you solve this, putting our force to be 0.3 from the question, putting our area now to be this one divided by 1,000, we can be getting it as 0.005. So when we solve that, we're getting this as our final answer. Our final answer will be 6 Newton per meter as surface tension. 6 Newton per meter as the surface tension of that material, of that liquid. So now let's go on to the next example, viscosity. The question says, if a fluid flows with a force of 5 Newton over an area of 0.2 meters squared and a velocity of 0.5 meters per second, calculate its velocity. Hello, can you guys still hear me?
Viscosity.
Hello. Okay, so let's go into viscosity. My network tripped off. So we have the question that says, if a fluid flows with a force of 5 Newton over an area of 0.2 meters squared and a velocity of 0.5 meters per second, calculate its viscosity. Calculate its viscosity. So now they gave us force, they gave us area, and they gave us velocity. So we're just to use this formula exactly the way it is given for viscosity, meaning viscosity is equal to force over area times velocity. And plugging and playing that, just checking here, we have area in meters, correct? Force in Newton, correct? Velocity in meters per second, meter, yes. Seconds, yes. So it's good. We can use everything the same way they are. So plugging that into the equation, we'll be having 0.2, sorry, 5 over 0.2 times 0.5. So I'm guessing our final answer to be 50 Pascal second. So that's the final answer for our viscosity for this question. I don't know if anyone has a question. Okay, so I think that should be straightforward. So let's head on to our next slide. I don't know if you guys can still hear me.
It says 50 Pascal per second.
Yeah.
Is the dot there represent per?
Not 50 pascals per second. It's 50 Pascal second. 50 Pascal second. So I don't know if maybe I'm taking it said Pascal per second. It was 50 Pascal second. So now we are going to our next slide, and we'll be treating now temperature and thermometry. Temperature and thermometry. So we know what temperature is. It's a measure of the average kinetic energy of particles. So some people say it is the degree of hotness or coldness of the body. So that is still correct, but that's actually like primary school kind of definition or junior secondary definition. So in real sense, it is a measure of the average kinetic energy of particles in a substance. So that's definition for temperature. So it's the reasonable definition for temperature. It's the measure of the average kinetic energy of particles in a substance. So it is usually measured with thermometer. So temperature is measured with thermometer. And we have different types of thermometer. We have mercury in glass thermometer, we have alcohol in glass thermometer, and we also have digital thermometer. So let's see the definition of these types of thermometer. So types of thermometer, we have mercury in glass thermometer. So this kind of thermometer is where we have the mercury would have a tube, a glass tube that will be filled with some quantity of mercury. So then as temperature is increasing, because mercury is a metal, but a liquid metal. So as temperature increases, the mercury begins to expand in length, begins to expand, even to small temperature increase, to begin to expand throughout this tube. So as it starts expanding, that's what we see as temperature. So they then calibrate this tube to then give different temperature degrees or different temperature scales. So that's how they make mercury in glass thermometer. So the same thing is the same idea is what is applied in alcohol in glass thermometer, because these two liquids, metallic liquid and alcohol, that's mercury and alcohol, they have high sensitivity for temperature change. They expand at low temperature changes. So the best of these ones for measuring low temperature is the best among these ones in measuring low temperature is mercury. So sorry, it's alcohol. So as you can see here, points. Alcohol has a low freezing point. So because of it has a low freezing point, it means it can be used to measure very low temperature. Very low temperature. So before it will freeze up and become stiff or become solid, it will take longer. You take it lower temperature before it can freeze up and become just alcohol block or alcohol ice block or alcohol block. Yeah, that's what it's called. So because of this, alcohol in glass thermometer is preferable in measuring low temperature, while mercury in glass thermometer is preferable in measuring high temperature, because alcohol, when the temperature goes very high, the alcohol will turn to vapor and you'll not be able to use it again, because once the alcohol converts from liquid alcohol to vapor alcohol, you cannot be able to see it or measure it, use it to measure temperature anymore. So for low temperature, they use alcohol. So this can come out in your exam question, 80%. They say which of these thermometer is best for measuring low temperature. So they will give you alcohol, they will give you some other funny names, but it's best for you to know that it is alcohol that is best for measuring low temperature. But one that is best for measuring high temperature is mercury. So because it has high boiling point, metals always have high boiling points. So before mercury will change to vapor, you need to take the temperature very high. So that's why it is good for high temperature measurements. But for low temperature measurements, when you're trying to measure something that's very cold, you would use what do they call it? Alcohol to measure temperatures that are very low, because alcohol will take time before it freezes. But mercury, if it gets cool to a particular level, it will become mercury solid, because normally mercury is a metal. So normally it wants to stay in solid state at low temperature. So that's why these two are used for these conditions. So now there is the modification of thermometer now came to become digital thermometer. Digital thermometer. So this thermometer is used for more accurate reading, and can be used for both extremes, both high and low temperature, both high and low temperature. So these are the examples or the types of thermometer. So if mercury, sorry, you said?
Sorry, sir, I'm not talking
Okay,
to
okay. If
you. But I
mercury
have
thermometer
question.
reads okay, go on. Let me hear it before we move on.
You said that if the temperature of mercury thermometer becomes low, it will form a mercury solid,
Yeah,
and as such will not be able to give us reading.
yeah,
Okay. What of
yeah. It will freeze up.
pardon?
Yeah, it will freeze up. It will freeze up. It will freeze up.
Okay, it will freeze off.
Yeah, it will
Okay,
freeze
what?
up when you take the temperature.
Okay. What of the alcohol at high temperature? What happens to it? Does it evaporate?
Yes, to evaporate. So when the temperature is up to 75, alcohol evaporates, because that's the boiling point for alcohol. So I think I've answered your question. Let's move on
Yes,
to
sir. Thank you.
okay, yeah, thank you. So let's move on to the next slide. Temperature scales. Temperature scales is the term that's used to talk about the different measurements or different parameters that are used, or different units that are used in measuring temperature. So they are called temperature scales. And we have Celsius, we have Fahrenheit, and we also have Kelvin. So I know most of the times we are used to Celsius and Kelvin. We are used to Celsius and Kelvin. So we know that temperature is to convert from Celsius to Kelvin, we just take 273 and add it to the Celsius conversion. It will give us the Kelvin conversion. So that's for Kelvin conversion. But for for Fahrenheit conversion, it's actually different. We have to use a formula that looks like this. This formula here, we can see here. This is formula to convert from Celsius to Fahrenheit and from Fahrenheit to Celsius. So the formula is just the same. It's just that they made F subject to formula in one of them and they made C subject to formula in the other one. So the formula is exactly the same. So it's just for you to know one of them and once you're looking for that one, just replace it, and know how you get your final answer. So now, for Celsius measurements, the lowest point or the freezing point of water, not the lowest point, the freezing point for water is going to be around 0.0 degrees Celsius, sorry. And the boiling point of water is going to be 100 degrees Celsius. For Fahrenheit, the freezing point of water will be 32 degrees Fahrenheit, while the boiling point of water will be 212 degrees Fahrenheit. But for Kelvin, sorry, I don't know whose mic is on. So for
Please,
Kelvin,
the freezing and boiling point of Fahrenheit.
yeah, that if you try converting 0 Celsius to Fahrenheit, it will give you 312. It will give you 32 Fahrenheit. If you try converting 100 Celsius using this formula here, to Fahrenheit, you will get 212 as your final answer. So that's the reason why it is not straightforward, is because of this fraction that's within the formula. So for that sake of that fraction, it's not stable comparing it to Celsius. So it has a kind of tweak in its expression. So just memorize. I think that's the only one that is difficult. It's not really difficult. It's a little bit tricky among the temperature scales. We have Fahrenheit, we have Kelvin, then we have Celsius. So from Celsius to Kelvin is simple. We know that 0 degrees in Celsius is 273 degrees in Kelvin. 273 degrees in Kelvin is 0 degrees in Celsius. So, but for Fahrenheit, it is different. It's different. The formula we'll use is this. So let's see how we use and we'll solve for converting Celsius to Fahrenheit.
What of the boiling point with Kelvin now?
The boiling point is adding 100 to 273. That's 373. That's the boiling point of water. 373.
Okay.
Yeah. So now let's see how to calculate to convert from Celsius to Fahrenheit. So to convert from Celsius to Fahrenheit, using this formula. Yeah, I can hear you.
So you said to convert to Kelvin, you do 100 times what?
100 plus.
Okay. 100 plus what?
So any degrees in Celsius, you add 273
the
to it.
melting point.
Yeah, you add 273.
100 plus the melting point, which is 373, which is the boiling point.
I didn't get you.
I'm talking to my fellow student.
Okay. So it's just if you want to change from Celsius to Kelvin, just take the Celsius measurements they gave you and add 273 to it. It will give you the measurement in Kelvin. So if they give you in Kelvin and say it's changed to Celsius, just subtract 273 from that reading. You will get the Celsius reading. So I think they gave you 373 Kelvin. Convert it to Celsius. Just subtract 273 from 373. So you'll be getting 100 as your final answer. So that's the value in Celsius. So it's simple to convert from Kelvin to Celsius. It's more simple comparing it to converting from Celsius to Fahrenheit. So that's why I'm giving an example of Celsius to Fahrenheit.
Sorry. To convert from Kelvin to Celsius, you do what?
You subtract the Kelvin reading from 273. You subtract 273 from the Kelvin reading. So if they gave you like maybe 500 Kelvin, yes, you subtract 273 from 500, you get this reading in Celsius.
Okay.
Is it clear? Yeah, so that's how it is.
Yes, then from Celsius to Kelvin, you do what?
You add the Celsius value.
You add to 273.
You add 273, yes. You add the Celsius value to 273, you get the Kelvin reading. Yeah.
Thank you.
So that's yeah, you're welcome. So let's go into the example. let's go into the example straight away. So we have convert 25 degrees Celsius to Fahrenheit. So now they gave us Celsius. So we should convert it to Fahrenheit. So we'll use the one that this formula. So we'll put in our Celsius value as C. Then just by putting that into this formula, we'll solve this by using our calculator. 25 times 9/5 plus 32 to give us our final answer as 77 degrees Kelvin and 77 degrees Fahrenheit. 77 degrees Fahrenheit will be our final answer.
I have a question. For the Fahrenheit,
Yeah, I can hear you. I can.
why are we using
Yeah.
why are we multiplying the Celsius by 9/5 and why are we adding it with 32?
There's actually a conversion constant 9/5.
Exactly.
So there's a conversion constant 9/5 that is
Universal
always going to be
accept.
multiplying C. So now this 32 is the lowest value. That 2 Fahrenheit is equal to 0 degrees. So the same way we use 0 degrees being equal to 273 on Kelvin angle, assuming there was no constant 9/5, it should have just been Celsius plus 3 plus 32 straight up. Then if you're doing it that way, it will be Fahrenheit minus 32 straight up. But because of that constant, that temperature constant, 9/5, that's the reason why we are putting in this. So it's just like as if you are putting C always has a 9/5 beside it. So we have to put it in every of the formulas. So even when C, we are trying to make C the solution formula, we have to still take account for that 9/5. So normally it's supposed to just be F equal to C plus 32. Then in the other way, it is going to be C is equal to F minus 32. But because of that constant, there's a constant, a conversion constant for converting from Celsius to Fahrenheit. That's why we have that 5/9 and 9/5. So why it is changing to 9/5 in one case and 5/5 in the other case is because of making C subject of formula and making F subject of formula. So when you switch this thing, it will change the fraction to 9/5 in one case and 5/9 in the other case. I don't know whether I've communicated something to you.
But two of them are the same thing now. To convert Celsius to okay.
It's not the same. They are different. So just the best thing is just know one of the formula, memorize one of the formula. I think the best formula to memorize is this first one. F is equal to 9/5 C plus 32. F is equal to 9/5 C plus 32. So now once you are given C to find F, that's what you use straight up. But once you are given F to find C, just put it in the formula and make C subject of formula, you get your C. Anyhow, you don't need to cram the formula, just know one of the formula and make subject of formula for which one you are trying to look for. So that's just it. I don't know if anybody still has another question because we've come to the end of this lesson. In conclusion, this lesson we've talked about the Bernoulli's principle, surface tension, viscosity, and temperature measurements. And I've showed you an example of how questions on these topics come out. So it's now your own duty to start going through these topics or looking for these topics in your past question app or in your past question, any of your past questions. Just look for this, what they call it, these topics. Then once you found the topics, try seeing how you can solve. Then once you've solved, if you get any hiccup, whether you are from Central Tutor Group or you are from I think everybody that is added to Central Tutor is also going to be on JUPEB General Group because currently we've not really launched outside. So everybody on Central Tutor is going to be on JUPEB Group. So any question you have that you need quick answer, just post it on the General JUPEB Group. For now, we've not shifted this thing brainstorming to, we've not shifted question to Central Tutor yet. So any question you have for now from Central Tutor or wherever on JUPEB, just go straight to the JUPEB group and paste it there. The tutor should be able to attend to it, or maybe one of your students too, or one of our students will be able to respond to you. So I don't know if that's clear.